Okay, here's a video lecture for section 14.1, reaction rates. So this is our introduction to chemical kinetics. Chemical kinetics is the study of how fast reactions take place. Many familiar reactions, such as the initial steps in fission and photosynthesis, happen almost instantaneously, whereas others, such as the rusting of iron or the conversion of diamond to graphite, take place on a time scale of days or even millions of years. Knowledge of kinetics is important to many scientific endeavors, including drug design, pollution control, and food processing. The job of an industrial chemist often is to work on increasing the rate of a reaction rather than maximizing its yield or developing a new process. A chemical reaction can be represented by the general equation, reactants turns into products, using the arrow, right? So it's often we're interested in the speed of a reaction. The equation tells us that during this course of a reaction, reactants are consumed, that means they're used up, while products are formed or produced. We can follow the progress of a reaction by monitoring either the decrease in the concentration of the reactants or the increase in the concentration of the products. So we can monitor either one to determine the reaction progress. The method used to monitor changes in reactant or product concentrations depends on the specific reaction. In a reaction that either consumes or produces a colored species, we can measure the intensity of the color over time with a spectrometer. A spectrometer is a device that measures the color of a solution. In a reaction that either consumes or produces a gas, we can measure the change in pressure over time with a manometer that measures pressure. That's a different way to measure what's going on. Electrical conductance measurements can be used to monitor the progress if ionic species are consumed or produced. So sometimes reactions occur in water and there are ions that are formed, so we measure electrical conductivity to see what's going on. So there's three different ways for monitoring the progress of a reaction. Average reaction rate. Consider the hypothetical reaction represented by A turns into B, in which A molecules, those are the reactants, are converted to B molecules, those are the products. Figure 14.1 shows the progress of this reaction as a function of time. So if you take a look at figure 14.1, what you're going to see is that at the beginning, when the clock is at 0, all of the little balls are gray. Those are reactant molecules. As time goes on, you'll notice that there are fewer and fewer of the gray balls, fewer and fewer of the A's, and more of the red balls, which are the B's. Those are the products. So A is turning into B. So by the time you get to the end, the last little figure on the right, you now have a lot of the B's, the red ones, and only a few of the grays. Those are the reactants. So we've converted much of the reactant into the product. So we're monitoring it over time, and that is an important, essential aspect of chemical kinetics, is that we make monitoring occur over time. Now, if we continue the reading, the decrease in the number of A molecules and the increase in the number of B molecules with time are shown graphically on figure 14.2. It is generally convenient to express the rate in terms of the change in concentration with time. Thus, for the reaction A turns to B, we can express the rate as rate equals the negative change in the concentration of A divided by change in time, or rate equals change in the concentration of B divided by change in time, where the change in the concentration of A and the change in the concentration of B are the changes in concentration in the units of molarity over a time period delta T. So the delta in this particular context, the symbol delta means change in. Okay, so it's the change in the concentration of A or B divided by the change in time. The rate expression containing change in concentration of A has a minus sign because the concentration of A decreases during the time interval. Remember, A is being consumed, so its changing is negative. That is, the change in concentration of A is a negative quantity. The rate expression containing the change in B does not have a minus sign because the concentration of B increases during the time interval. Right? It's increasing. Rate is always a positive quantity. We define rate as positive. So when it is expressed in terms of a change in a reactant concentration, the minus sign is needed in the rate expression to make the rate positive. So notice there, we want the rate to be positive. When the rate is expressed in terms of the change in the concentration of the product, no negative sign is needed to make the rate positive because the product concentration increases with time. Rates calculated in this way are average rates over the time period delta t. So look at the graph, the two graphs actually in figure 14.2. The one in red is the product, right? That's B. The one in blue is the reactant, that's A. Notice that as you go increasing time, that's on the x-axis, A is decreasing. The blue one is getting smaller, right? It's being consumed. B, that's the red one, is increasing over time. So there's the little dots there. Those dots are measurements that were made at 10, 20, 30, 40, 50, 60. It's not clear they measured it at 0. There's no little dots at 0. Presumably there would be dots at 0, but they're not showing them. The curves that are being drawn in are just there to connect those dots. Okay? So we didn't make the measurement every second. We made the measurement every 10 seconds. And then we drew in a curve to connect those dots just so that you can sort of see visually what's going on. Okay? The y-axis is the number of molecules. That's how many molecules we have. Now notice in the text it says that we're really going to deal concentration, not number of molecules, but concentration. So the graph isn't showing you concentrations. It's just showing you the number of molecules. But what we'll find is that if we were to plot concentration over time, the graphs would look the same. So they're just showing you the number of molecules. So figure 14.2 is really a continuation of figure 14.1. Now, to understand rates of chemical reactions and how they are determined, it is useful to consider some specific reactions. First, we consider the aqueous reaction of molecular bromine, Br2, with formic acid, HCOOH. The chemical equation is Br2 aqueous plus HCOOH aqueous forms 2Br minus aqueous plus 2H plus aqueous plus CO2 gas. So that's the chemical equation for this reaction of bromine reacting with formic acid in water. Remember, AQ means water. Molecular bromine is reddish brown in water, that is, whereas all other species in the reaction are colorless. As the reaction proceeds, the concentration of bromine decreases and its color fades, figure 14.3. The decrease in intensity of the color, and therefore in the concentration of bromine, can be monitored with a spectrometer, which registers the amount of light absorbed by bromine, figure 14.4. So we can see with our eyes, but if we want to do more specific measurements, more accurate, we're going to use a spectrometer instead of our eyes. Our eyes can just really tell us qualitatively, oh, that's a deep color or a light color or no color at all. But we need a spectrometer to make real measurements. So figure 14.3, the caption says from left to right, the decrease in bromine concentration as time elapses is indicated by the loss of color. See what's happening there? The bromine's getting used up, so the color is going away. And if we measure how fast that happens, we're going to get the reaction rate. Now, we're going to scroll down to figure 14.4. This is data shown for a spectrometer. The spectrometer, you may have used that in the previous course, Chemistry 11. A spectrometer measures absorption, essentially the amount of light that gets absorbed by the sample. And you can plot it versus wavelength. Remember, wavelength is a property of light, it's a property of electromagnetic waves. For visible light, it is often in the units of nanometers, nm. It's a measure of essentially how much energy the photons have. So from 300 to 600 nanometers, which is in the ultraviolet range and the visible range, you can see that the bromine is changing its absorbance. At T1, it's very, very high. That means there's a lot of bromine in there. At T2, it's reduced by about a half almost. And then at T3, it's even smaller. So what's happening is the absorbance of bromine is decreasing with time. And we're going to use data like that to measure kinetic properties. Figure 14.4. This is the caption. Plot of the absorption of bromine versus wavelength. The maximum absorption of visible light by bromine occurs at 393 nanometers. By the way, 393 nanometers is not really visible light. It's considered UV, although it's very close to visible light. So that's tricky. As the reaction progresses from T1 to T3, the absorption, which is proportional to the concentration of bromine, Br2, decreases, right? The reaction's occurring, so bromine's decreasing. Absorption will decrease, therefore. Measuring the bromine concentration at some initial time and then at some final time enables us to determine the average rate of the reaction during the time interval. So this is where we're going to get into the nitty-gritty here of the arithmetic of kinetics. Average rate can be defined for this reaction as the negative change in the concentration of Br2 divided by the change in time. Remember, that's from our earlier discussion where we talked about the negative change in the concentration of the reactant A divided by the change in time. So we're using bromine because that's the substance that absorbs light, so we can monitor it. This rate, this average rate, is equal to the negative of the final concentration of bromine minus the initial concentration of bromine divided by the final time minus the initial time, delta T. Delta is the quantity you're measuring. Could be time, could be concentration. Final minus initial. So the final time minus the initial time. Using data from table 14.1, which is below, we can calculate the average rate over the first 50-second time interval as follows. So look at that table, 14.1. I'm going to scroll down a little bit here so we can see it. There's a set of data here, table 14.1. Rates of the reaction of molecular bromine and formic acid at 25 degrees C. So if you look at that data, there's a bunch of time points from 0 to 400 seconds every 50 seconds. There's also a concentration of bromine in the units of moles per liter, molarity. Notice the bromine concentration decreases over time, time increases over time. Then there's a set of rates that are given here. So where do these rates come from? Well, I'm going to show you how to get one of them. We're going to use two data points. We're going to use the first two, actually. Time equals 0 and time equals 50 seconds, respectively. So the average rate would be the negative of 0.0101 molar minus 0.0120 molar divided by, now they don't show it, but it's 50 seconds minus 0 seconds, right? It's final time minus initial, so it's 50 minus 0, which is equal to 50. If you take that ratio, and I highly recommend you follow along these calculations with a calculator, you should get 3.80 times 10 to the minus 5, and the units would be molarity over seconds. Now, they're being kind of sloppy here. The numerator is in molarity because that's concentration. The denominator is in seconds, so that should be divided by seconds. They just didn't put it in the textbook here. And they didn't put 50.0 minus 0.0, so they're being kind of sloppy. But if you do it correctly, you'll get 3.80 times 10 to the minus 5 molarity per second. Why is it positive? There's a negative in the front, right? But 0.0101 minus 0.0120 is negative, so the negative of a negative is positive, so the average rate will be positive. Now, below it says if we had chosen the first 100 seconds as our time interval, the average rate would then be given by 0.00846, so that's at 100, minus 0.010, that's at 0. That difference divided by 100 minus 0. Again, they're being a little sloppy here. It should say 100 seconds minus 0 seconds. That will give you 3.54 times 10 to the minus 5 molarity per second. Now, these calculations demonstrate that the average rate of this reaction depends on the time interval that we choose. In other words, the rate changes with time. That's an important aspect of kinetics. The rate changes over time. We're going to talk more about that in future sections. This is why a plot of the concentration of a reactant or product as a function of time is a curve rather than a straight line. So take a look at figure 14.5. The plot of bromine concentration against time is a curve because the reaction rate changes as bromine changes with time. B, the plot of the reaction rate against bromine is a straight line because the rate is proportional to the concentration of bromine. So that's an important aspect. The concentration of bromine versus time is not a straight line, it's a curve, but the rate divided by the concentration of bromine is a straight line. Rate versus concentration is a straight line, linear. Okay? Now, I will point out that the two values that we calculated do not appear in the chart. They calculated their own rates for different times, specifically at those times, so that's why those numbers don't show up. But if we pick the values in the first two columns and calculate them the way we did, the values we get, 3.80 times 10 to the minus 5 and 3.54 times 10 to the minus 5, those values will show up. Now, let's get into what's called the instantaneous rate. If we were to calculate the average rate over shorter and shorter time intervals, we could obtain the instantaneous rate, which is the rate for a specific instant in time, not averaging over 50 seconds or 100 seconds, but an instantaneous rate, like what the rate is at a specific time point. It'd be almost like you were watching someone run a 100-yard dash or a 100-meter dash, and you said, okay, well, I'm going to figure out how fast they're moving by measuring the amount of time it takes for them to run the 100 meters. So I'm going to take the 100 meters and divide that by the time. That would be the average rate of their speed. If you wanted their instantaneous rate, what would you do? You would use like some sort of laser beam to measure how fast they're moving at a specific instant in time. For most of us, we're probably running faster after 20 meters than we are at 100 meters because we're going to slow down over 100. Most of us can't run 100 meters to our full capacity for the whole time. We're going to poop out at the end. But if you look at a track star, they're probably running just as fast at 80 or 90 meters as they are at 20 meters because they've trained for it and they've learned how to maximize their speed the whole way. So their instantaneous rate will jump up really rapidly at the beginning and then be relatively stable over the next 70 or 80 meters, maybe fall off toward the end, but maybe not. I'm not exactly clear on that. It's a good question. But for most of us, we would slowly get faster. We'll go fast for a while, then we'll poop out, and by the end, we're like going real slow because we're too tired. Okay? So this is really the idea of instantaneous. How fast are you moving right at one specific time? We would use maybe a laser gun to do that, a radar gun. Now, for chemical kinetics, we can measure the concentration very, very precisely over time. So we'll get something like we talk about here. The instantaneous rate is equal to the slope of a tangent to the curve at any particular time. Note that we can pick any 2 points along the tangent to calculate its slope. For a chemist, the instantaneous rate is generally a more useful quantity than the average rate. For the remainder of this chapter, therefore, the term rate will be used to mean instantaneous rate unless otherwise stated. So look at the graph 14.6. I'm going to read the caption. The instantaneous rate of the reaction between molecular bromine and formic acid at 100 seconds, 200 seconds, and 300 seconds are given by the slopes of the tangents at these times. So now we have a discussion of the slope of the tangent. The idea here is the following. If you look at the points that are plotted in this graph, there's 1, 2, 3, 4, 5, 6, 7. Looks like there's 9 points. One at 0 seconds and the last one's at 400 seconds. See what they did? They took the curve, which they drew in after they drew in the points. So you do the points first, then you draw in the curve. That's the blue line. Then they say, what's the rate at any point along that curve? What they did was they said, okay, I want to know what the slope is, or I'm sorry, I want to know what the rate is at 100 seconds. So they drew a straight line that barely touches that point and doesn't touch any other points along the curve. So that's the red hypotenuse of the triangle. So at 100 seconds, at 2.96 times 10 to the minus 5 molarity per second, that's at 100 seconds, they drew a straight line with a ruler or a computer program, and then that gave them a line, the red line. Then they drew a triangle out of it. How did they do that? Well, where the red line is on the left, they drew a vertical line coming down, and where the red line is on the right, they drew a horizontal, and they constructed a little triangle there. And then they figured out the slope of that. The slope is the height of that triangle divided by the length of the triangle. So the height divided by the length, that ratio is the slope of the line that they drew at that point. And so that ratio gives you the slope. And from that slope, it's called the slope to the tangent. It is called the slope of a tangent to the curve. That is essentially the rate at that point, the instantaneous rate. So let's go through the calculations so you can see where this comes from. The slope of the tangent, and therefore the reaction rate, diminishes with time because the concentration of bromine decreases with time. The data in Table 14.1 show how the rate of this reaction depends on the concentration of bromine. At 50.0 seconds, for example, when the concentration of bromine is 0.0101 molar, and the rate is 3.52 times 10 to the minus 5 molarity per second. When the concentration of bromine has been reduced by half, i.e. reduced to 0.005 molar, at 250 seconds, so look on that curve at 250, the rate is also reduced by half, i.e. reduced to 1.75 times 10 to the minus 5 molarity per second. Therefore, concentration of bromine at 50 seconds divided by concentration of bromine at 250 seconds is about equal to 2. And the rate at 50.0 seconds divided by the rate at 250.0 seconds is equal to 3.52 times 10 to the minus 5 molarity per second, divided by 1.75 times 10 to the minus 5 molarity per second. That's approximately equal to 2. So, thus, the rate is directly proportional to the concentration of bromine. The rate is proportional to the concentration of bromine. The rate is equal to K times the concentration of bromine, where K, the proportionality constant, is called the rate constant. Rearranging this preceding equation gives that K is equal to the rate divided by the concentration of bromine. We can use the concentration and rate data from Table 14.1 for any value of t, time, to calculate the value of K for this reaction. For example, using the data for time equals 50 seconds gives K equals 3.52 times 10 to the minus 5 molarity per second. That's from Table 14.1, divided by 0.0101 molar. That would be equal to 3.49 times 10 to the minus 3 reciprocal seconds at 50 seconds. Likewise, using the data for time equals 300 seconds gives K equals 1.48 times 10 to the minus 5 molarity per second divided by 0.00420 molar. This would be equal to 3.52 times 10 to the minus 3 reciprocal seconds at time equals 300 seconds. Slight variations in the calculated values of K are due to experimental deviations in rate measurements. To two significant figures, we get that K is equal to 3.5. So look at that, 3.49 and 3.52. It's equal to 3.5 times 10 to the minus 3 reciprocal seconds for this reaction, regardless of which line of data we chose from Table 14.1. It is important to note that the value of K does not depend on the concentration of bromine. The rate constant is constant at constant temperature. In section 14.4, we will discuss how K depends on temperature. So the point of this is what I would say. The rate depends on the concentration of bromine. As the concentration of bromine gets smaller and smaller, the rate gets smaller and smaller. You can tell that from the curve. The slope of the tangent to the curve gets smaller and smaller as you move on in time, and that's because the concentration of bromine is getting smaller. The rate of a reaction depends on the concentration of the reactant. As the concentration of the reactant gets smaller, the rate gets smaller. However, if you take the ratio of the rate divided by the concentration of the reactant, you get K. That's the rate constant. It doesn't change with time. It's constant with time, essentially. Therefore, there is a constant called K, and that will be constant. Now, we now consider another specific reaction. So this is a second reaction, the decomposition of hydrogen peroxide. Now, the reason this one is picked will become evident in a moment. 2H2O2 aqueous, which is dissolved in water, that's hydrogen peroxide. You probably have some of that in your medicine cabinet. It forms 2H2O liquid plus O2 gas. Because one of the products is a gas, we can monitor the progress of this reaction by measuring the pressure with a manometer. Okay, you may not know what a manometer is. It's covered in Chem 11 somewhat. It is a device used to measure the pressure of a gas, okay? It measures the pressure of a gas. Pressure is converted to concentration using the ideal gas equation. Guess what? Pressure of a gas is related to concentration. PV equals nRT. This is the derivation. Or pressure of O2 equals N divided by V times RT. N divided by V is concentration. So that's the concentration of O2 times RT. So where N divided by V gives the molarity of the oxygen gas, rearranging the equation and solving for the concentration of O2, we get concentration of O2 is equal to 1 over RT times the pressure of O2. The reaction rate, which is expressed as the rate of oxygen production, can now be written as, remember, O2 is a product, right? So there's no negative. Change in the concentration of O2 over the change in time equals 1 over RT times the change in the pressure of O2 divided by change in time. Okay? So here we go. We now have another way of measuring the rate of a reaction, in this case a product, but it's because oxygen is a gas and a product. Let's come up to the next reading. Determining the rate from pressure data is possible only if the temperature in kelvins at which the reaction is carried out is known. We have to know the temperature. Take a look back over here at this equation. See how you have T, temperature in the denominator? You got to know what the temperature is. Figure 14.7 shows the apparatus used to monitor the pressure change in the decomposition of hydrogen peroxide. Shows the plot of oxygen pressure, PO2, versus time. As we did in figure 14.6, we can draw the tangent to the curve in figure 14.7 to determine the instantaneous rate at any point. By the way, they don't do that here. They're just saying they could. They're not going to go into great detail with this one like they did with the previous one. So let me show you figure 14.7. Here's the caption. A, the rate of hydrogen peroxide decomposition can be measured with a manometer. That's the manometer right there. See, it's hard for you to tell, but there's a big meter stick vertically mounted on a ring stand. And there is a mercury glass tube that is connected to the meter stick so that you can measure the height of the mercury. If you recall from Chem 11, when you have a gas, you can measure its pressure using a mercury manometer. The height of the mercury gives you a measure of the pressure of the gas. So that's what they're doing here. So the reaction is occurring in that glass flask. See the yellow solution? And then it's connected. The top is connected to this mercury manometer, the mercury tube, to give you a pressure measurement of the oxygen gas. So as oxygen is produced, essentially what happens is it pushes down on the mercury more and more and more, so it changes the height of the mercury, and that gives you a measure of the pressure of the oxygen. Now, if you look at figure 14.7b, see what's happening? The pressure is going up. Why? Well, oxygen is a product, so its pressure is going to increase over time, not decrease. It's not a reactant. Okay, now let's continue reading. Stoichiometry and reaction rate. For stoichiometrically simple reactions of the type A goes to B, the rate can be expressed either in terms of the decrease in reactant concentration with time, the negative delta change in A divided by delta T, or in terms of the increase in product concentration with time, comma, delta concentration of B divided by delta T. Both expressions give the same result. For reactions in which one or more of the stoichiometric coefficients is something other than 1, we must take extra care in expressing the rate. For example, consider again the reaction between molecular bromine and formic acid. Br2 aqueous plus HCOOH aqueous gives you 2 Br minus aqueous plus 2H plus aqueous plus CO2 gas. We have expressed the rate of this reaction in terms of the disappearance of bromine. But what if we chose instead to express the rate in terms of the appearance of the bromide ion? That's one of the products, okay? According to the balanced equation, 2 moles of bromide, Br minus, are generated for every mole of Br2 consumed. Thus, bromide appears at twice the rate of bromine disappears. To avoid the potential ambiguity of reporting the rate of disappearance or appearance of a specific chemical species, we report the rate of reaction. In other words, we generally don't talk about how quickly something disappears, one of the reactants, or how quickly something appears, the product. We want to get the same speed for any substance, so we define it in terms of the rate of the reaction. We determine the rate of the reaction such that the result is the same regardless of which species we monitor. For the hypothetical reaction A turns into 2B, the rate of reaction can be written as either rate equals the negative change in the concentration of A divided by the change in time, or rate equals 1/2 times the concentration of B, change in concentration of B, divided by the change in time, both of which give the same result. So remember, putting that negative and then dividing by 2, that gives you the rate. So what you do is you look at the coefficient of the species and you put that in the denominator. So if the coefficient is a 1, you just put a 1. If it's a 2, you put a 2. If it's a 3, you put a 3. So you divide by that number. If it's a product, you don't put a negative. If it's a reactant, you do put a negative. And that will ensure that you get the rate no matter what substance you're talking about. For the bromine and the formic acid reaction, we can write the rate of reaction as either rate equals negative delta concentration of Br2 divided by delta T, as we did earlier, or rate equals 1/2 times the change in the concentration of bromide divided by the change in time. In general, for the reaction A plus B goes to C plus D, where we have lowercase a, b, c, d as the coefficients, uppercase are the chemical species, the rate is given by, now take a look at what they did. They're dividing by the lower cases, A, B, C, D. They're multiplying by negative if it's a reactant and no negative if it's a product. So it's the negative 1 over A, where A is the coefficient, times delta concentration of A over delta T. Same for the second reactant, B, but no negative if it's a product. So that way we can write the rate for any species in the equation. Expressing the rate in this fashion ensures that the rate of reaction is the same regardless of which species we measure to monitor the reaction's progress. Okay? Take a look here. Sample problem 14.1. I'm going to go over that problem in a separate video. Same with sample problem 14.2. I'll do that one as well for you. And then there's these checkpoints, okay? So this one has quite a bit of an introduction in terms of the reading. A lot of reading in here. But the main thing is to go over this reading, read everything very carefully, and then we're going to do the practice problems.